It's not as like fun and great as it looks like. It actually takes a long time, and it's just I'm not sure why I can't see it.
Yeah.
It's not focused.
What is it for? I swear I'm not breaking it. Here we are. Okay, so this part here is ash. This is one of those clay aggregates. You can kind of see it.
What is the clay there? It's kaolin or is it
So I didn't source it. So I don't know what clay it is because I don't have the entire spectrum. And because I don't have loose samples. If I went back, I would take loose. This idea came after we already impregnated the samples of doing it this way. So this is a sample that has layers. We saw it before, layers of red ash, ash and clay down here, layers of pure ash, and that huge chunk of charcoal with bone. So we'll just find one piece of clay. We'll take an image, and then we'll take the background.
Stage, there's on this stage inset there's a 13 millimeter hole. You could get a different stage inset. Most people do FTIR, and then you don't need the tube hole, and so that's why I haven't bothered to get a different stage inset. But yeah, you can map up to about the size of a business card.
And so once the background is taken, and then it takes each point, it just subtracts the background automatically when it gives you the spectrum. That's not true for all of the FTIR machines. Ours doesn't at VU. You have to manually tell the software to subtract the background. Yeah.
So your aperture size looks like it's 150 microns, and is that a typical size? Is the box in the middle, is that the aperture size? The
box in the middle is the aperture size, and it's adjustable. The smallest aperture you can set is about 10 microns, and that's just because of the diffraction limit of light. The hole is smaller than the wavelength light won't go through. For transmission, the largest stage, there's on this stage inset there's a 13 millimeter hole. You could get a different stage inset. Most people do FTIR, and then you don't need the tube hole, and so that's why I haven't bothered to get a different stage inset. But yeah, you can map up to about the size of a business card.
And so once the background is taken, and then it takes each point, it just subtracts the background automatically when it gives you the spectrum. That's not true for all of the FTIR machines. Ours doesn't at VU. You have to manually tell the software to subtract the background. Yeah.
So your aperture size looks like it's 150 microns, and is that a typical size,
You
box,
can-
the box in the middle, is that the aperture size?
The box in the middle is the aperture size, and it's adjustable. The smallest aperture you can set is about 10 microns, and that's
But
just
it's
because
not-
the diffraction of light. If the hole is smaller than the way light won't go through. For transmission, the largest you
There you go. So, ash, and bone right here. So this is. Should I reset the stage to clean the ATR? No, just next. So we want.
Nice clean tissue, there should be a bottle of isopropyl alcohol, toss envelopes, because
Yeah.
as I showed, fuel oil has its very nice spectra of its own.
As you saw.
So ATR crystals can come from the bottom or from the top. It doesn't matter fundamentally. From the bottom, it's easier to do liquids and powders. So if you have a powdered sample, you don't have to grind it and stick it in a KBR pellet. You can simply press it onto an ATR crystal that's from the bottom. This particular system is really designed to do mapping, and so having it come from the top and be able to go along the sample works well. So measure background according to aperture.
The next.
So the background now is just going to be against the air. So the ATR is lowers, and then we did a background measurement just against the air to correct for the unevenness in the intensity of the glow bar at different wavelengths, and for the water vapor and carbon dioxide. So we made dramatic demonstrations of carbon dioxide by gently blowing the sample right now, and you get huge carbon dioxide.
Well, this is Ronnie. Can I ask a question about the clay? I just thought of. So I have thin sections of rubified soil that
Yes.
we think is probably a heart. This would, by running a series, that would confirm it if I saw a loss of peaks in that region.
Yeah.
Great.
It should.
Just
Yeah.
gotta get one.
It should. Just consider the fact that the deeper you go in the hearth or combustion feature, the less the clays are going to be changed by the heat. So if you take a sample, a really good example of this is actually a paper by Stephanie Sims and Berna on clay balls that were used for cooking in Mesoamerica. She saw that the clay balls, which are literally, Franco, like this big, like just like a fist big, were heated in the fire and then put in water to make the water boil. But you can actually see in this small of a clay, the part that was in direct contact with fire, way more heated, and this little piece, there's like literally a few millimeters of the surface that was just not exposed to direct fire, but still in the fire. It has a different, you can definitely see the difference in degrees. So that is something that you really need to consider. And then if it's a hearth that has been out for a while, then you have to consider rehydroxylation of the clay, so those hydroxyl bond could come back. There's a lot of literature on that as well. and there's a 2016 Forget article that also talks about they found that there are differences in how you fire if you fire clay in a
basically
reduximorphic is the word that I have in mind, but it's not the right one. More oxygen or no oxygen.
If you have a massive sediment, the best rule is if you're gonna analyze it for heating, you want to take it along what you can most likely presume to be an exposed top surface, because that's where you're going to get the least effects from just the thermodynamic nature of the fire moving up. That's where you're going to get the least, that's where you're going to be in the most contact with the fire. You're going to be the most oxygenated in terms to atmospheric levels of oxygen, and you're going to be suffering the least amount of insulation from surrounding sediments. So you're going to be, that's going to be most true to the actual temperatures of the fire that was on that surface. Because like she said, if you vary from that, and that's why using the slide is important, because it allows you to target areas where you can have some control over those factors of exposure to heat.
If the hearth is in situ and you take an in situ block, then you can definitely go and target the highest, the contact, rather than getting loose samples, bringing it back to the lab, and then at that point it's just mixed together.
I was thinking of the thin sections and how you're parlaying optical microscopy with this technology. I mean, we can define the clays optically, and then at least to a degree, and then define the firing temperature.
Yeah, and then
if you have shells or soil carbon, it adds significantly to the number of thresholds that you can look at for heating. Aragonite particularly, so if you have snail shells, it adds a lower threshold of about 350, which can be useful in looking at sort of unengineered wood fires. This is something that I've done. It's a little trickier because the aragonite to calcite heat transformation is actually a range between 350 and 450, but you can model it to assume temperatures around 350, 400. And then if you have just soil carbonate, then you have a couple more thresholds at and above 700 that you can look at.
So the bone spectrum came out as a heated bone, or slightly heated bone. It seems to be consistent because we have the appearance of this peak. So that is that apatite peak that we were looking at, and we have this one at 1096 that is starting to appear, and we have that at between 500 degrees that appears. So I would say, and in fact, if you look at this bone optically, it looks orangey yellow brown, right? It looks like it's being in contact, direct contact with fire, and I wanted to show you that it does come out if you actually have a heated bone. It does come out. How are we doing on time? 45, and we have. Oh, I'm way over. I'm sorry.
Okay.
Oh, done.